The fourth problem from today's weekly contest, we're given a tree which is not a binary tree, it can have multiple, more than two children. Okay, and we are asked, and we are given edges. For every edge, we have a weight, and we are asked to remove the necessary edges so that every node is going to have at most k edges, that is k other nodes, and we have to remove it in such a way so that after removal, the remaining edges, if we do a sum of the weights which are remaining, then that will be maximum. It's maximized, right? So if this is the tree, we have 0, 1, 3, and 4 having only two edges, which is good, but 2, node 2 is having three edges, which is greater than k. So it needs to let go one edge. Which one will it let go? Well, it will let go 2 as the edge because after removing that we will have 22. That's the maximum, and that's why 2 is removed. So if we generalize it, right, if we think of this problem like something like this, then suppose if k is equal to 2, in that case all these uh, nodes are valid because they only have one edge, but the middle edge is not valid because it has three edges. Its degree is 3, which is greater than k. So it needs to let go one edge, right? It can let go this edge, it can let go this edge, or it can let go this edge. So it has a choice. Similarly, suppose this was 1. In that case, this guy needs to remove either these two or after parent any one of the child, right? So that's the thing. So we need to keep track of the, so by track I mean that will be a state at our dynamic programming argument, and that state will be, is parent edge removed or not? It is removed or not. So this will be one state, right? Okay, so let's look at another thing. Suppose this is a tree. I'm doing it for two children. We can then generalize it for multiple children. Suppose k is equal to 1. In that case, it needs to let go one edge. Okay. Which one will it let go? This one or this one? It depends, right? Suppose this edge has a subtree, or this particular node has a subtree which has x1 as its weight after uh, you know removal of this edge. Actually not. X1 is the value if we include this edge, and y1 is the value if we exclude this edge. Similarly, this guy has also a subtree which gives x2 as the value if we include this edge, and y2 as the value if we exclude this edge, right? So by that I mean if we include this edge, that means we are already excluding this edge. So excluding this edge and this particular subtree's weight will leave to x2, and same goes for the other values. So if we are given this, then if I ask you for the entire tree, what is the value that is going to be If we exclude this edge, that means we are including this edge. So that means in that case, if we are including this edge, then x1 minus y1 is a value which represents this one, which we are excluding. That means it's a minimum value, right? That's why we are excluding. So it should be lesser than x2 minus y2, right? So basically, I can generalize it for multiple children, right? For every children, what is the value if we exclude this edge or include this edge, x's and y's, I and yi, and if I generalize it, I'll need some kind of this kind of inequality in order to determine which all uh, edges needs to be removed first among all the other children, right? So in that case, I will take xi minus ii for all the children. I'll sort it based on this value, and after that, I will remove the top xi minus yi values, the uh, top few values, and that few values depends on this particular node's degree minus k. So this particular node's degree is 1, 2, 3, 4. Just for this example, 1, 2, 3, 4, 4, right? If k is 1, in that case, 4 minus 1 number of edges I need to remove. That means 3 x minus yi values, which are at the top or the bottom or the most minimum, right? Since we are sorting it from in ascending order, the lowest three values, that is the lowest degree minus k values, needs to be removed from this one, right? That's all we need to do. And after removing the remaining ones, we need to sum it up, get the answer, right? So let's go to the code and write few pointers. The second thing is get x I and yi with parent, without parent, sort based on xi minus yi, remove the top degree minus k values, or not the top, the bottom degree minus k values, or let me write it like the smallest degree minus k values from the list of xi minus yi, and finally sum the remaining values, whichever is maximum among xi or yi, right? After removal of the unnecessary or the removed edges, the remaining I will choose among xi or yi. I can't choose both, right? One represents with parent, one represents without parent. So it represents two different things. I can't choose both of them at the same time, right? That's wrong. So I will choose the one that is maximum since I need to maximize. So let's get into the code. Firstly, I'll get the n, and that n will be, since edges is of length n minus 1, I can have edges dot size plus 1. right? I can have a adjacency list that will be built using edges, and since we have weight as well, the source, destination, and weight, so we will have three things, right? So we will need a 3D adjacency list of size n. Alright, so for every edge, I will push it inside the uh, adjacency list. This will be undirected graph, so I'll push it in both ways. The first thing will be the destination node. Second thing will be the weight. Okay, and this is undirected, so now it's destination to source as well. Okay, and now I'm going to call the dt function. Let's call it solve pass adjacency list. The first thing we need is the node where we are at. Uh, the second thing is also we are going to need k, right? So that we are able to determine how many nodes needs to be removed. So let's pass k. And the next thing we will be that we'll be needing is the parent, right? For every node, so that we don't process. So if we have this node, we don't know, what is its parent. So for that, we are going to pass parent as well, so that we don't go revisiting the same thing and get stuck in a TLE, infinite loop. So let's pass parent. So initially, since the parent or the node will not have any parent, so let's oh, this should be 0. The node is 0 initially, and its parent is also 0. All right. The last thing is this one. Uh, let's not call this state since we have other things. This one. All right. States. The first thing is the node parent and is parent edge removed or not. It should be 0 initially, or 1, or yeah, 0 since it is not removed. That's it. That's our TP function. And since it's going to be long, let's define. Yeah, let's define long here. Okay, let's have the TP function. The first thing will be the adjacency list, which will be a 3D DP. So vector of n, and that will be passed with reference. The first thing is node. The second thing is the parent. The third thing is parent edge removed. Okay, and since we don't have a base condition, we can just start right away. Uh, so first thing is we need to get, you know, the value or the number of edges that we need to remove from the current node, right? How many edges do we need to remove? That will be number of edges to remove, which is nothing but uh, the degree of the current node, that is adjacency node dot size, which is going to be the degree of the current node, right? Minus k, right? Like I said, degree minus k is going to be the number of nodes that we need to remove. But since If is parent edge is removed, then we are already decrementing it by 1, right? If it is not removed, then we are good. So if it is removed, since it's going to be 1, I can just subtract it. If it is not removed, it's going to be 0. It's not going to affect this. And last thing is, this can be negative, right? Suppose it only has 3 edges and k is 4. In that case, this can go negative. In that case, I don't need to remove anything, right? It's already less than the number of edges. I need to maximize the possible weight. So I need to consider all the edges. So in that case, if it is negative, I need to remove 0 edges. So I will take the maximum and that will handle all the cases. So next thing is we are going to build the list which is going to contain the children, right? The values of the children, that is xi minus yi or xi comma yi. That's what is going to contain for every children. So it's going to be a list which will be containing xi comma yi, which will be both long. So let's have ll comma ll, and here take not take on children. So it's going to be take, let's name it take not take children, since we are taking or not taking their parents edge and having the values x comma y. So let's call it take not take children. Okay, take not take children, initially empty for all of their children, which is nothing but a iteration over the adjacency node. And if the adjacency or the neighbor node, that is their children, is equal to their parent node, then I don't need to consider that. So if it is not equal to parent, in that case, get the take value, get the not take value, and push it inside the children. Here it will be take value, and here it will be not take value. Alright. So for the take, I am going to consider uh, the edge from the node to the neighbor, right? Which means neighbors for first index, not the zeroth index. Zeroth index is the destination, right? So neighbors first index is the weight which I'm going to take, and I'm going to call the sort function for the remaining adjacency list with neighbor with the neighbor as the current node, right? Which is nothing but neighbor 0. K will be still K, so oh, I'm not taking K here. Let's correct it. Here I'll pass K. Now the parent node will be the node itself, and the is parent removed? No, it is not removed because it is taken. So this will be 0. And similarly for the not take, since the parent is removed, it will be 1, and all the other things will be same. We don't add anything since we are not taking it, and that's pretty much it. Here we are going to sort the vector, and that will be based on the x minus y value. So let's have a comparator where LHS comma RHS is going to be based on LHS, which is x1 y1. So x 1 will be LHS dot first minus Y1 will be LHS dot second should be less than RHS dot first minus RHS dot second, and that's it. So now I have the children, so I'm going to iterate from the remaining, or I have all the children, so I'm going to, since it's sorted, the minimum uh, number of edges to remove value, or the minimum number of edges to remove count children is going to be uh, removed, right? So it's not going to be considered, or it's going to be considered inside the answer, right? For the remaining edges, yeah. So for these many edges, I'm going to use the not take value since I'm going to remove that edge, right? So let's iterate. Since I is from 0, so if I is less than this value, in that case, sum the answer with the values of not take, which is nothing but dot second, else sum it with the values whichever is maximum, right? Because we need to consider the remaining values whichever is maximum among xi comma yi. So dot first comma dot second, and that's pretty much it. Let's return the answer and see if it works. We are going to minimize it. We have okay, we have some problem since this is size is going to return iterator, that's why it's wise to convert it to int. If neighbor is not equal to parent, that means the destination, so it should be 0 and not just neighbor. Okay, it works. Let's minimize it. We have three states. We have two states, node and is parent edge removal. We don't consider parent as another state because node is going to take care of parent, right? We don't need uh, two states for the same parameter or similar parameter. Let's have a 2D cache. Let's have vector int, call it cache. Here resize it with what value? Node can be of n size, so let's have n plus 1 comma vector of int is parent edges removed can be 0 or 1. Let's have 2 initialized with minus 1. So at this point, if cache of node and is parent edge remove is not equal to minus 1, return the value because it is contained inside, and otherwise every time you return answer initialize it. Let's see if this works. The time complexity will be n of n since we have just one state, and the space complexity will be, okay, we have some issue since we have long values. Let's have ln instead, and that should fix it. Okay, this should be LL as well, my bad. This time complexity will be ofn since we have just one state, since the other state is just of size 2, and the space complexity will be ofn again. That's the fourth problem. Thanks.